Hi class. In this recorded lecture, we will talk about transformer performances. Basically, we have two main parameters to determine the performance of our transformer. These are transformer efficiency and transformer voltage regulation. So, kailangan nato ma-determine ang performance sa ato ang transformer. It's because it is part of maintaining the overall health of our transformer. So transformer is one of the most expensive and important components in our power system. That is in the case of large transformers, and for small transformers, we can find it in numerous applications, smaller electrical applications, and even in even smaller electronic components. So, regardless of the size, kailangan na to ma-determine ang efficiency and voltage regulation sa atong transformer because failure to do so can result to overall system failure. So, kung dili na to na ma-diagnose at an early stage ang na dili na di ay nindot ang performance sa atong transformer, then mas costly, expensive, and kana bitang irrevocable ang damage na pwede mabuhat sa ato ang failed transformer. So to start with, ang efficiency is basically the ratio of the output divided by the input. This can be in the form of power output or energy output versus energy input. So ratio between supplied energy and the energy drawn or demand from the transformer. So, efficiency directly affects the aging and performance of transformers. Kung bago pa ang transformer, we can expect the transformer to operate at a higher efficiency, or kung dili bitaw overloaded ang transformer, we can expect that it performs well in terms of efficiency. Pero kung nakadugay na gayong transformer, ma-expect ta na mas mababa o mababa ang iyang efficiency. And tolerable or healthy range sa atong efficiency is between 95 to 99%. There are three components sa pag-determine nato sa atong energy losses sa transformer, because calculating the losses is important rather sa pag-determine sa atong efficiency. Kaya mao man ay what do you call this? Ang output is basically equal to input minus losses. So as much as possible, i-reduce na to ang losses in order to achieve greater efficiency sa atong transformer. Ang losses, we have first ang core loss. So this is independent of the load, and this is equal to the open circuit power on the transformer test, which is done under no load conditions. So na-discuss na to itong transformer test, makita na to dito si open circuit power. So mo na siya basically ang atong core loss. Second is ang atong copper loss, which is equal to I squared R losses, as some textbooks would refer it. And this is due to the resistance of the winding. So this type of loss is basically dependent on the magnitude of the load, the transformer load. And then third is the stray loss. We have stray loss as the eddy currents induced by leakage flux. Pero sa ato ang calculation, sa atong sample problems later, we only have copper loss and core loss. And the formula that you can see in the screen is basically the formula that we will use in the efficiency, but not this equation 3.1.1, because we will use a bit simplified approach, or more straightforward formula later on ako i-introduce sa sample problems. But right now, we will talk about voltage regulation. Voltage regulation of a transformer is the change in the magnitude of the secondary terminal voltage from no load to full load, and is usually expressed as a percentage of the full load value. So, ang regulation, again, in other definition, it measures how well a transformer can maintain constant secondary voltage given a constant primary voltage and wide variance in load current. So, atong transformer, dili na to na siya i-expect na kana bitong fixed na ang load na iyahang gina-serve. So there are times nga kanang gamay lang ang load, there are times nga dako pod ang atong energy load, and that corresponds to a change in voltage or terminal voltage sa atong transformer. So there is a range of values or range of change from no load to full load voltage na matolerate sa atong transformer. Anything that goes beyond that can be dangerous or risky sa ato ang transformer health. That's why important po na itakal nato ang regulation in order to determine if and when ang ato ang transformer energy load is still operating within the operational limits of our transformer. So the lower the percentage or closer to zero at ang percent voltage regulation, the more stable the secondary voltage and the better the regulation it will provide. Ang formula sa voltage regulation is given in equation 3.1.4. So no load voltage minus full load voltage divided by a full load voltage. And natay alternative formula po sa itong voltage regulation given at equation 3.1.6. So it's just a matter of computing ning mga what they call this coefficients. But right now, we will try to solve quite a few sample problems actually kay ang makita nato dari sa atong sample problems is kana bitaw murag combination of many things that we can solve at a given set of data for our transformer. Say for instance kaning a problem which tends to solve quite a few parameters from our practical transformer with load. At the same time, it gives us an opportunity to solve the efficiency of this particular transformer. So for a single phase 60 Hz transformer rated at 500 kVA, 2,400 volts to 480 volts, the equivalent circuit impedances in ohms are, we have R1, R2, XL1, XL2, our line impedances composed of resistance and reactance. We have the core reactance of 2000 ohms and the magnetizing core resistance rather of 2000 ohms and magnetizing reactance of 500 ohms. So this is a loaded transformer. The load connected across the low voltage terminal draws rated current at 0.8 power factor lagging with rated voltage at the terminals. So first, let's calculate the high voltage winding terminal voltage, current, and power factor. So ang una nga step ani class is to attempt to draw the equivalent circuit diagram of our transformer so as to realize kung unsay itsura ani mga circuit impedances and where they are located in the transformer. So what I am drawing right now is man siyang ginatawag nga T equivalent or Thevenin equivalent nga transformer diagram. So man siya ang ato ang R sub 1, wani siya atong XL sub 1, then wani siya atong R prime sub 2, then wani siya atong XL prime sub 2. So kanina mga prime, wani siya ang kanabitong secondary line impedance which is referred to the primary. So kani siyang tibok diagram is wani siya ang equivalent circuit diagram referred to the primary. Then to finish man siya ang core conductance, then we have the magnetizing susceptance which is basically ang reciprocal lang sa resistance o reactance as we learned it from circuits 1 or 2. So to start with, ang transformer our turns ratio na to is from 2,400 to 480, that is equivalent to 5. So in order to solve R prime sub 2 and XL prime sub 2, we have a squared R2 and a squared XL2. So, solving that using ang A is equal to 5 and katong values sa line reactance, line impedance sa secondary winding, we have 0.075 ohms and 0.3 ohms. Muna siyang equivalent nga what they call this line impedance referred to the primary. Now, let's try to solve the current drawn by the load, or in short, load current, which is still referred to the primary. Magbutan lang ko apostrophe for to represent that I apostrophe sub 1. We have the kVA rating divided by the terminal voltage, the what you call this kanang rated voltage to the primary. So we have 500 kVA, 500 VA, then we have 2,400 volts. Ma-cancel ang voltage, then it will leave us with 208.33 amperes. Next is isolve na to ang power factor angle ani nga current. We have power factor or cosine theta is equal to 0.8 sama sa gisulti sa problem. Then ang angle na to is negative cosine of 0.8, and that is equal to 36.87 degrees. So man na siya ang angle sa to ang load current referred to the primary. We have 208.33 at negative 36.87 degrees amperes. Negative 36 degrees because lagging ang atong power factor. Then next that we will solve is descending end voltage. So ang sending end voltage na to nga formula is given dito sa practical transformer with load na lesson. We have V1 is equal to E sub 1 plus I apostrophe 1 times the equivalent line reactance. And our E sub 1 is asama sa rated 2,400 volts plus 208.33 angle negative 36.87. I-times na to na siya with asa naman to 0.075 plus J 0.3. Mana siya nga to ang gisolve kani dare ang equivalent na impedance. So atong V1 is equal to 2,500 volts. I-neglect na lang ako ang angle, kaya angle is just around 1.9 degrees, which is fairly negligible. So mana siya tong V1, it is 2,500 volts. Then let's solve for current. But before we can solve the overall current drawn by our transformer and its load, we need to solve for I sub O first. So I sub O is equal to I sub C plus I sub M. So balik ta sa diagram, mani siya si I sub O, kani si I sub C, then kani si I sub M. Kailangan nato na ma-determine ang mga currents para ma-solve ang core, ang current na ginadraw sa transformer core. So kani siya na mga formula, IC is equal to GC E1 and IM is equal to BM E1. Gikan ni siya dito sa katong lesson na to about ideal practical transformers without load or no load. So palihog lang ako review atong material in order for you to get familiarized with the formula. So this is equal to E1 divided by RC, then kani siya is equal to E1 divided by XM. So 2,400 divided by 2,000 given is a problem, then 2,400 divided by 500, and our IC is equal to 1.2 amperes and our IM is equal to 4.8 amperes. Pero ang sum ani niya is we will express in vector quantity. So 1.2 minus J 4.8 amperes. So mapansin niyo na naka-vector quantity siya 1 for 1. And second is naka 1.2 minus or negative siya. It is because naka-parallel na sila. So it is treated as parang negative good kaning sign. So we have our IO. So we can solve now for total current. We have I is equal to I sub O plus I apostrophe 1. We have 1.2 minus J 4.8 plus atong current ganina nga 208.33 angle negative 36.87. So our overall value of I is 202 angle negative 37.7 amperes. So mana na siya ang value sa itong current. Then power factor is given at cosine kung unsa ng angle sa itong current, dapat ang angle sa current ang itong basehan. Cosine 37.7 is equal to 0.77 power factor lagging. Magbutang dyan tag-apelyado ang atong power factor kung lagging ba na siya, leading or unity. Depende sa kung unsay angle sa to ang power factor or angle sa current sa to ang phasor diagram if we were to draw a phasor diagram. So man na siya atong power factor. So that's just the first part, I believe, kaning letter A. Now let's go to letter B, wherein we will solve for the transformer efficiency. We have efficiency. So to start the solution, we will first solve for output power. Ang output power nato is equal to katong rated volt ampere niya, which is 500,000 or 500 kVA, 500 VA times ang load na ginadraw at 0.8 power factor. This way dapat makuha na to ang real power output, which is in this case 400,000 watts. So ang pag-calculate to sa efficiency, it would be better if naka-express siya in watts or real power, because oftentimes ang atong losses or power losses are expressed in watts. So just for consistency. Next thing to do is we will solve for losses. Yan. We have first is the copper loss. This is equal to our short circuit power equal to I squared R, I1 squared Req or equivalent resistance. Then kato na-solve na to ganina, 212 squared. Then ito ang equivalent resistance is 0.135. So atong copper loss is equal to 6,067.44 watts. Sama na siya. Indicate lang nato losses PSC and so atong core loss karon is equal to the open circuit power or POC. So formula from the previous lesson, ang open circuit power nato is equal to conductance, core conductance times the square of the voltage. So ang conductance is reciprocal sa katong core resistance. We have basically 1/2000 times ang voltage natong na-solve previously, which is 2,500 ang sending end voltage, squared of that voltage. So ato ang core loss is equal to 3,125 watts. So mala na siya ang duha ka losses na itong ma-solve. So ang total losses nato is equal to 6,067.44 plus 3,125, which is equal to 9,192.44 watts. So ma-compute na nato karon ng efficiency. Itong efficiency is given by 1 minus losses divided by output minus losses. Output plus losses. This is equal to 1 minus atong losses is 9,192.44. Output nato is 400,000 plus losses again is 9,192.44. Atong efficiency is equal to 97.8%. Please don't forget to express this in percentage because we're talking about efficiency. So mani siya to ang efficiency. And that's just for our first problem. Next example that we will solve is a transformer problem that involves regulation, voltage regulation to be specific, and efficiency. The parameters of this transformer, 150 kVA to 2,400 to 240 volts transformer are kung saan ninyo makita dare. Okay. Using the circuit referred to the primary, determine the voltage regulation A and B efficiency of the transformer operating at rated load with rated voltage of 240 volts and 0.8 power factor lagging. So the problem specifically tells us to use a transformer equivalent circuit referred to primary. So this is what I've done in the previous example. Kato siyang transformer T circuit or T equivalent circuit is referred to primary. So ako naanad lang ko nga puro in terms of primary ang transformer na akong gina-solve. Then, of course, kanya kong gina-drawing is mo ni siya ang katong sa core nga part. So, as usual, mo ni siya tong R sub 1, mo ni siya tong XL1. Then, kani siya, mo ni siya tong secondary impedance referred to primary. Then, mo ni siya ato ang conductance, susceptance, which is mara po niyang mga equivalent. And ang ato ang transformer at turns ratio 2,240 volts is 10. So para ma-solve na to ang mga R prime na values nato, we have to multiply that with A squared. So makuha na to na siya with 0.2 ohms, then 0.45 ohms. So, mani siya itong kinatawag nga referred to primary. Then, nanatay impedances referred to primary, makabuhat na ta og line impedance values. Makuha na itong values sa itong line impedance, equivalent line impedance. We have REQ 1 is equal to R1 batias akong R R1 plus kana then atula na siyang i-add class. We have for equivalent resistance 0.4 ohms, then equivalent reactance as 0.9 ohms. Then the next thing that we can solve is that basically we can start on solving the voltage regulation. Ang formula na akong gamiton karon is something na wala na ko nahatag sa handouts. But I'm just gonna explain this in this recorded lecture anyway. So before tamo proceed sa formula, we will solve for the angle first, which is the arc cosine of 0.8, which is equal to 36.87 degrees. Then we have the load current referred to primary to be 150,000 VA kung sa tong rating sa tong transformer divided by the high voltage rated voltage. Cancel ang V, then we have 62.5 amperes. Muna siya ato ang load current. Then ang atong ang pag-solve nato sa voltage regulation is mo-solve ta sa no load current, no load voltage. So VNL, kaya ang full load voltage theoretically is mo na to siya tong rated voltage na to, which is 240 volts. So ang no load voltage referred to primary, so VNL1, we have E sub 1 cosine theta plus I sub 1 REQ squared plus or minus E sub 1 sine theta plus I sub 1 X reactance, equivalent reactance squared. Tanan na siya inside A square root. So, pwede ta mag-solve in either primary or secondary secondary winding, pero kani siya is referred to primary because we are consistently using values from the primary winding. Then you can either use primary or secondary values as long as it is consistent. Tapos kani siya nga part, kani plus or minus, plus na siya kung lagging ang atong power factor, load power factor, then negative kung leading. So mana siya tong timailhan dira. This is a really handy formula, daw taas lang siya tan-awon pero dali lang kay siya timan-an. So continuing with the solution, we have atong E1 2,400, then cosine of 36.87 plus atong I sub 1 load current referred to primary is equal to 62.5 times atong equivalent resistance which is 0.4. Tanan sa sulod sa square plus sab na po ta 2,400 sine, this time sine of 36.87 plus ang load current of 62.5 times equivalent reactance of 0.9 squared. So simplifying that further, we have 1,945 squared plus 1,496 96.25 squared. So itong no load voltage sa primary side is equal to 2,454 volts. So since na naman tayo no load voltage, tas ang full load voltage na to is kung sa to nasa rating, we can now solve for the percent voltage regulation by no load voltage minus full load voltage divided by full load voltage. So we have 2,454 minus 2,400 divided by 2,400. So atong percent VR is equal to 2.3%. So it's not bad per se because it is just a small amount. So nanatay VR. Ang next na to isolve according sa problem is ang efficiency sa transformer operating at rated load with rated voltage of 240 volts and 0.8 power factor lagging. So letter B, we will solve the transformer efficiency. So to start the solution, we have to solve for the ascending end voltage first. So balik-balik na siya nga formula referring to primary side. We have V1 is equal to E1 plus load current divided by the line impedance. The equivalent, we have 2,400 plus 62.5 angle of the power factor angle of 36, negative 36.87 times the line impedance equivalent 0.4 plus j 0.9, and our V1 is equal to 2453 volts. Next that we will solve is the output power. Solve for output power. Assuming full or rated load. So output is getting the real power from the apparent power, which is 150,000 volt amperes times ang power factor of 0.8, we have 120,000 watts. Ano siya itong output? Now, solving for losses, remember we are solving for efficiency. Atong copper loss is equal to I sub 1 squared REQ. So we have 60 we're supposed to have 61.8 tare, not 62.5. 61.8 squared REQ of 0.4. So this is equal to 1,527.7 watts. Tapos ang core loss nato is equal to core conductance times the square of the voltage, and our conductance is equal to 1 over 10,000 times atong voltage ganina nga 2453 volts, and that is equal to 601.7 watts. So total loss is simply the addition of the sum of copper and core loss, which is in this case 2,129.4 watts. Therefore, solving for efficiency, we have 1 minus losses over output plus losses. This is equal to 1 minus 2129.4 divided by 120,000 plus 2129.4. Our efficiency now is equal to 98.26%. So, mana siya ang final value sa itong efficiency. I will box it in red. Pero, ang wala na ko na-appeal sa solution dari class is kani siya, in which mag-solve ka dapat sa IO is equal to IC plus IM. Then, atong I1 is equal to IO kani siya by the way is dapat vector sum sama sa akong gibuhatong previous example, then kining IO plus tong load current I sub 1 I apostrophe na siya is also a vector sum. So para makuha ninyo si 61.8, nani siya sa previous example nga process. Para masubay ninyo ang process. So mana siya ang pamaagi sa pag-solve na to, so regulation and efficiency. Then moving on to our third problem, we have a 3 kVA 220 volts to 110 volts what do you call this transformer, still 60 hertz single phase transformer, yields the following test data. So we have the open circuit test and the short circuit test. So sa previous lesson, na hibalaan nato kung unsay equivalent sa open circuit current, voltage, and power, as well as sa short circuit voltage, current, and power. So refer to, what do you call this, to lesson 3 para sa interpretation na niya. Then the problem asks us to determine the efficiency when the transformer delivers a load of 2 kVA at 0.85 power factor lagging. So you have to take note na ang rating sa transformer is 3 kVA, and yet i-determine na to ang efficiency when the transformer delivers a load of only 2 kVA. So that entails na ang transformer usahay is mo under mo perform below sa iyahang rating, which is still good as long as dili mas maayo man na mag kanang bitang below the rating kaysa above the rating ang operation sa transformer. So we have to determine the efficiency if the transformer operates below its rated power. So we will explore the process of how this solution will look like. So since efficiency man, magsugod ta og solve for output power. We have output or P out is equal to, let's use the 2 kVA kay mama na siya ang condition, 2000 volt amperes times ang power factor na 0.85, therefore natay masolve nga 1700 watts nga power output. Now solving for losses, we have two losses. First is ang copper loss. Fortunately, this is equal to the short circuit power or PSC. However, sulat nila na ako dari, copper loss is load dependent. Remember class sa akong previous nga discuss ganina, ang load current, atong copper loss is dependent sa load. That's why it is also termed as load loss. So in order to come up that, Ang copper loss ato is equal to short circuit power. Let's say we will come up with two equations. So ang atong copper loss or short circuit power, our copper loss PCU G, which stands for given, which is in this case 2 kVA, is equal to the given current squared times Req. So thankfully si Req is constant. Then we have the copper loss nga rated, so we have PCUR. R stands for rated, is equal to rated current squared times Req. One siya tong 1, equation 1, then one siya tong equation 2. Now, combining 1 and 2, we have PCUG divided by PCUR is equal to IG squared Req divided by IR squared Req. Karon i-multiply na to na siya with V squared over 1,000, then V squared over 1,000 pod sa baba, so that we can come up with the kVA rating of with the kVA values na sama sa giun sa paghatag sa given, just for consistency. So atong given, ato ang corresponding na copper loss para sa given nga 2 kVA can be solved using the rated copper loss kung sa tong given sa ato ang short circuit test na power. Only that we need to multiply it with the ratio of kVA given divided by kVA rated squared. So man siya tong gamiton karon na formula para ma-solve ang ato ang corresponding change in copper loss. Solving for PCUG, we have PCUG equal to 30 kay may given sa ato ang short circuit power times ang given na kVA at which is 2 kVA divided by the rated kVA which is 3, then squared. So ang ato ang power karon is isulat na lang ako in fraction 40 over 3 watts. Then ang ato ang core loss is core loss or PC, which is equal to the open circuit power, will remain constant. Remains constant. So we will carry that over. Constant siya class because core loss according here is independent of the load. So bahala kung sa ang load, ang core loss is constant. Now solving for efficiency, we have 1 minus losses divided by output plus losses. Alternatively, this can also be expressed as output divided by output plus losses. So I'll use the latter. We have output 1770 sa itong pagka-solve ganina. Then output again plus ang ato ang copper loss, then atong given na core loss which is 50. So atong efficiency DI is equal to 96.5%. So still within the range of 95 to 99%. our transformer is still on good operating limits. So inaana siya class in cases nga kanang i-determine na to ang efficiency if the transformer operates outside of its rated power rating or kVA rating. Then the last of this series of solved problems would involve a bit of a combination among what we have discussed so far. So the problem tells us that a 75 kVA 230 volts to 115 volts 60 hertz transformer is still provided with both the short circuit and open circuit test results. So again, same sa previous example, nani siya yung mga equivalent, just to refer to lesson 3 for the formula sa katong transformer tests. Then we have to determine 3 things. Number 1 is voltage regulation at the rated load and 0.8 power factor lagging. Next is the efficiency at rated load 0.8 power factor lagging and the efficiency at half load unity power factor. Then the third is the maximum efficiency and the current at which it occurs. So ang bag-o lang dari nga sample problem is ang katong maximum efficiency. So we need to solve for maximum efficiency, and the importance to do so is para mahibala na to kung unsay maximum na efficiency sa transformer. So ang motivation sa na to sa maximum efficiency is para mahibala na to kung unsa ang conditions sa unsa dapat ang power output, unsa dapat ang current na mag-result as our load current in order to achieve the maximum efficiency that the transformer can operate. Mas ma-maximize na to ang paggamit sa transformer that way. So for the first part, kaning voltage regulation, we can voltage regulation. We can solve for REQ and XEQ from the short circuit test. So isulat lang nako. So again, refer na lang mo dito sa transformer test nga lesson. In order to look for the formula. So we have REQ is equal to the short circuit power divided by the short circuit current squared. Short circuit power na to is 1,200 watts. Then atong short circuit current is 326 amperes squared. So we have an REQ of 0.0113 ohms. Then before na to masolve ang XEQ, moagi sa ta sa ZEQ first. And our ZEQ is equal to the short circuit voltage divided by the short circuit current. So 9.5, that is divided by 326 amperes, and that is equal to 0.0291 ohms. So, kuha lang ni siya Pythagorean theorem kay resultant vector man na si z. So, para ma-solve si equivalent reactance is the square root of zeq squared minus req squared, and that is approximately equal to 0.0268 ohms. So, nanatay req ug xeq. So, kailangan natin siya ma-solve aron makasolve ta sa tong voltage regulation which will start by solving the no load voltage. So, katong angle pa di ay from the power factor of 0.8 is equal to 36.87 degrees. So, solving for voltage regulation, referring to primary side, we have V and L is equal to E1 cos theta plus load current I sub 1 Req squared plus E sub 1 cos sine plus I sub 1 load current xeq squared. So, laging man ang power factor, so kailangan natin magamit og plus. So, kana si I sub 1, basically, equal na siya to the short circuit current. Okay, rated, man na siya, ang short circuit current is kanang rated current na mag-result gikan sa kanang rated kVA niya. Then, substitute na to ang mga values. We have 230 kanang VE1 cosine of 36.87 plus I1 326. Req na to is 0.0113 squared plus 230 sine of 36.87 plus again 326, then ato ang xeq which is 0.0268, all of that squared, then still under sa square root. So, simplifying, we have 187.68 squared plus 146.74 squared, and our no load voltage is equal to 238.24 volts. So, since na natin no load voltage, masolve na nato si voltage regulation. So, that's V and L minus VFL divided by VFL. So, we have 238.24 minus 230 divided by 230, and that is equal to percent VR nato is equal to 3.58%. So, na-solve na nato si letter A. Next to solve is ang letter B. So, isolve na nato ang efficiency at two conditions. So, letter B, Sulatan ako efficiency. Efficiency when kani rated load and 0.8 power factor lagging. So medyo straightforward lang taan eh. Output is equal to 75,000 VA times ang power factor nga 0.8, and that is equal to 60,000 watts. So mana siya ang output power nato. Then from the given, we have ang copper loss nato is equal to our short circuit power, and that is equal to 1,200 watts. Then we have our core loss, which is equal to our open circuit power, and that is equal to 750 watts. So masolve na dahil na to ang efficiency niya. Efficiency is equal to output divided by output plus losses. So output na to is 60,000 divided by 60,000 plus 1,200 plus 750. So our efficiency is equal to 96.85%. That is only for kaning rated load and 0.8 power factor lagging. For the next condition, we have efficiency at half load and unity power factor. So pag unity power factor, ang atong output is equal to ang output nato is half sa load daw, so we have 75,000 volt amperes divided by 2 times 1.0 ka unity ang power factor, so natay 37,500 watts. That is for the half load. Then as we have discussed kanina, atong PCU is dependent sa load, so magbuta na lang ko PCU half is equal to PCU rated times KVA half divided by KVA rated squared. So atong rated na copper loss is, what do you call this, 1,200 watts divided by 37,000 37,500 divided by 75,000, or simply 1/2 squared. Then ato ang PCU half is equal to 300 watts. Then PC or core loss is equal to POC or open circuit voltage, which is still 750 watts. So nanatay losses, makasolve na ta sa efficiency. Output is equal to over output plus losses. So we have output 37,500, then again 37,500 plus 300, which is atong bago nga copper loss, plus 750, constant lang ang core loss. 750. So atong efficiency in this case is equal to 97.28%. So half load di ay mas dako siya gamay kesa sa katong rated load lang na kanang operation. Mas dako ang efficiency kung half load. Then for the third part, we are supposed to solve for a maximum efficiency. Sulat lang nako maximum efficiency. So naatay condition para ma-achieve si maximum efficiency. So isulat lang nako nga in order for maximum efficiency to occur, so dapat ang open circuit power nato or atong core loss is equal to the short circuit power or copper loss. So i-obey na to ang value sa open circuit power or core loss. Okay, mao man na siya constant. So in this case, ang open circuit power is equal to 750 watts. So automatically mo po na dapat ato ang copper loss. So remember nga i-obey na to ang value sa open circuit power or core loss kay mo man na siya ang constant. Again, obey na to ang value sa open circuit or copper loss, open circuit power, kaya mo na siyang constant. So, the next thing that we will do is to solve for I1. Para ma-solve na to ang current at which the maximum efficiency occurs. So, I1 is equal to, no. So since copper loss is equal to I1 squared Req, I1 then is equal to copper loss divided by Req squared. So that is equal to 750 divided by 0.0113 squared. So itong I1 is equal to 257.63 amperes. So I will just box it in red box. So this is the current at which maximum efficiency occurs. Then let's continue with the usual process of solving the efficiency. So output is equal to rated power times the ratio of the open circuit power with that of the short circuit power. In this case, use original values para ma-determine na to ang ratio. So this is a new formula actually. Ako na lang i-box. And atong rated power is 75,000 VA divided by the square root of 750 divided by 1,200, and that is equal to, ang output nato is equal to 59,292.7 volt amperes. $59,292.7 volt amperes. So, na naman tayo value sa output and losses. We can now solve for the efficiency or the maximum efficiency. Ako lang i-distinguish as N max. That is equal to output divided by output plus 2 times core loss. Kaya ang core loss man natong gi-obey. So we have 59,292.7 divided by 59,292.7 plus twice of 750. So itong maximum efficiency is equal to 97.53%. Isulat lang ako. So mana siya class. Just take note of the new formula na nag-pop up sa ato ang solve problems because it is helpful para ma-solve na to ang next few problems. Okay?